Here's another typical Newton's Law problem here where they describe a box here, and the box here has a mass of 550 kilograms. And they ask you a variety of questions. The box here is hanging by a rope that has a tension T in it and 50 kilogram mass. So they ask a variety of questions about what the tension would have to be under some various scenarios about the box's motion. So in the first one in A here, they want to know what would the tension have to be if the box was at rest. In other words, if V is equal to 0. And they also imply that the box is also going to stay at rest, so it's just never going to move. What would the tension have to be? Well, of course, what's not drawn in the problem that you have to remember about is the box has a weight which pulls down like this, and the weight is always equal to m times g like that. And so if you want the box to stay at rest for all times, then that implies here that the y acceleration on the box has to be equal to 0. Okay, this a sub y has to be equal to 0 if v sub y is equal to 0, and we want it to stay at 0. How are you going to pull off an a sub y equals to 0? Well, you may or may not know intuitively how problems like this work, but if you have no idea how to proceed with something, just go with Newton's law. Sum of the y forces divided by m. And if you want this y acceleration to be 0, you'd put a 0 in for this. Sum of the y forces divided by m. And now if I can solve this for the big sum here, we get, okay, look, the sum of the y forces are going to have to equal to 0 if I want this a sub y to be equal to 0. That's going to have to happen. What y forces do I see on this block? Well, I see a tension up and I see a weight down. So I can go ahead and fill in the sum here. And I'll get a plus t minus an mg is equal to 0, or the tension is equal to mg. Put a big circle around that. So the tension would have to be equal to weight if you wanted to maintain a 0 acceleration, a 0 y acceleration, which is going to maintain v sub y is equal to 0. The tension would exactly have to balance the weight. In the next part of the problem, in part B here, they want to know what would the tension have to be to maintain the box moving up at a steady 5 meters per second. So steady here is a key word in these problems here. Steady implies this 5 is always going to be the same number. It's not going to change. So this is very much like part A. If you want to keep it at 5 meters per second, once again, the acceleration must be 0, because accelerations are what change velocities. My guiding equation in that sort of logic here, again, is that v is equal to v naught plus a times delta t. It's equation 2 here. If you want v to always be equal to v naught, if you want this v to be the same, a must be 0. So that's what we're saying. If we're going to stick at 5, we're not going to change. The tension must once again be equal to the weight. That's the way to maintain a constant speed like that. Part C says, now what if the box is speeding up with a y acceleration of 5 meters per second squared? So it's going to speed up. It's being pulled up and it's speeding up now. Okay, so now it will have a y acceleration on it. So you can take this form of Newton's law again, this useful one here that we're going to use here. We're going to say, okay, the 5 here then is going to be the sum of the y forces divided by m. And so the sum of the y forces on this block, then must be the required 5 meters per second squared. That's the acceleration that we're shooting for, but I'm solving for m, so now I multiply by m, and there'll be a big 50 over here, 50 kilograms. So there's the a times the m, if you will. So what y forces do I see in the block? Well, once again, just like last time, I do see a tension up, and I do see a weight down like that, and all that's going to be equal to this number here, this 250 newtons on 5 times the 50, the 250. So you can solve for the tension now, and you'll get that it's 250 newtons plus the mass, plus the weight of the object, pardon me, not the mass, the weight of the object, the m times the g. So the m is about 50, and g is about 10, so this is another 500 here. So it looks like you're looking at about a 750 newton tension to keep the box moving up with the acceleration that is required there. Kind of an odd thing, well, the tension has to exceed the weight, so tension is not always equal to mg the way this problem was here. And then that's definitely true. If you want to make this box go up in such a way that it actually keeps gaining speed, you will have to pull on it in such a way that you have to exceed the weight of it to give it a net force upwards, which gives it a net acceleration, which allows the velocity to change. So that does happen. Tensions can exceed weights of objects that they're connected to, although common sense typically tells you that whenever something is connected to a block, whenever a rope is connected to a block, the tension must be mg, but that's not true if the object is accelerated. Part D of the problem is really the same, but it just says, what if the acceleration now is minus 5 meters per second squared? So what the minus sign actually implies is, yes, the acceleration has changed signs, but now you're trying to slow down, trying to slow the block down. So why is it negative? Because it's moving up before with a positive velocity, because positive is up like that. So if we want to slow it down, we need an acceleration in the other direction. And that's what this sort of equation implies here, that you're going to slow the thing down. It doesn't change the problem very much. In fact, you'll have the same analysis is actually this part right in here, if you can recall where that came from, only now the 5 is going to be a negative 5. So all told, when I work sort of the same, do a lot of the same logic here, we just have a sign change, but we'll get that T minus mg, there's that weight on there again, is equal to minus 5 times 50. And so the tension that I'm going to get now is going to be mg, just solving algebraically. I still have the mg in there, but I won't have a plus 250 anymore. I'll have a minus 250 in there. So the tension now actually has to go below the weight value in order to get that negative deceleration. So in other words, we want the weight to be the dominant force to cause the acceleration to be downwards a bit. So we have to pull on it a little bit less than the weight in order to get it accelerate downwards. In fact, 250 newtons less than the weight to get the required acceleration. So there's another case there where the tension is not equal to the weight, but that's the dynamics of the problem. We want it to accelerate downwards at minus 5 meters per second, or in this case here, upwards of 5 meters per second. But you see two cases here where the tension is not equal to the weight.